So a new small subsection of the course on principal component analysis. And so start by explaining that today. So that will be covered over the next 2 weeks. So just to wrap up stuff on the schedule. So homework 3 is going to be due on Wednesday. So so the people here who's almost finished the homework, and how many of you have not started the homework yet? So I've officially warned you that the last question is meant to be a little tricky, but there should be a simple solution that you can do if you don't have without doing the advanced. But make sure you do that before it's too late. So if the homeworks are there to help you reinforce things that we're that we're learning in class, and if you kind of wait for the very last minute on them, you might not be able to get as much out of it. So we just finished the Euclidean Descent section in the course, and so part of that was in homework 3, and then the part about doing Euclidean Descent on actual data, there'll be a question about that will come out in homework 4. Homework 4 will be posted probably by the end of this week, and then will be due towards the end of November. So then in this week, we'll be lecturing about PCA and the SPD, and that will continue on with some stuff next week. I will be traveling next week, so the TAs will actually give the lectures. So one of the lectures will be on how to actually compute the SPD. So using the power method, and so Ben Way, one of the TAs, is a PhD student here, and this is something he's done research in. He's an expert in this area, so he should be very informed on this topic as well. So I think they'll be in good hands in the stuff next week when I'm not with you. So we're going to be talking about principal component, analysis. Okay, so this is often just called PCA. And so today's lecture will be basically explaining what this is and give you a starting point towards solving that. So kind of the input here is going to be a data matrix. We'll call this A, which is going to be an element of n times d. Okay, so an n by d matrix. And the goal here, and I'll mathematically specify this goal, is going to be to find a low-dimensional a low-dimensional subspace which captures the data in A. So we're going to think of this data point is going to be a data matrix. Okay, so I'm calling this a data matrix, and I'll explain. I'm going to give some examples, and then I'll explain why I just called it data matrix instead. So we're going to think of this as being n points in RD. Okay, so they're going to be so these n d-dimensional points, right? So if we have this matrix A, right? This is the matrix A. Then each one of these rows, so this is going to be D columns and N rows. So each of these rows will be AI, and this will be a d-dimensional vector, right? So this is going to be in RD. Okay, and so we have n of these different data points. Every row is a data point. They're each going to be a d-dimensional vector. Okay, and so examples of this could include, so if you think you have n, say, weather stations, so, and you have d, so time points, right? So then, and so like each value aij is going to be temp, is going to record the temperature at station I at time j. Okay, so this would be an example. So I'm going to have, I'm going to collect data in this way, where there are these kind of n different stations. Each station is a data point, and that each column is going to be some time I'm collecting data. I think maybe as time goes on, I'm collecting more and more of these columns, but the number of stations stays fixed. Or maybe I have some historical history I'm interested in measuring, and I keep finding more and more stations, and I can grow the matrix this way. All right, so this is one example. So I can also have 10 movies, and I'm going to have D people. So this is like a recommendation system, and so AIJ is going to be a rating of the movie. So typically a rating might be, say, between 1 and 5, where 5 is better. This is a long time how these been rating, but you could think of this as being continuous value in some range. So this is a problem that's common to things like Netflix and Amazon. They want to make some recommendation for, if a bunch of people like the movie, then each of those, then that movie has a high rating. But maybe there's a different subset of specialized subset of people who tend to like this movie. You want to understand the different categories of movies, and it may not fit exactly in a category. It may fit between categories, and you get these sorts of model issues. Okay. You could also model like a stock price, and so you have T. So time points of this stock. Okay, so I'm going to have and each time point it's going to have the price value of the stock up to time uppercase T. And so one way how to turn this into a matrix D is that I'm going to take these groups of time points and look at how it's moving over time. So the first D time points is going to be one row, A1 in this matrix. And then the next row in the matrix, TD plus 1, is going to be shifted over by 1. So I'm not kind of decomposing it into different pieces, but I'm shifting it. It takes every d consecutive time points. So this would be A2, and I would do this up to AT minus D. So here, I'm going to get that the number of time points minus D is equal to N, and D is going to be the number of time points in, this might be called a shingle, right? Like shingles on a roof, they kind of overlap in this way. Okay, so I would turn this into a matrix in this way. So then the full matrix would be a stacking of these rows. Okay, and this is often used in trying to predict what the next value will be. Right, so a lot of economic models are built on something like this, where I take d consecutive things and I'm trying to predict what the next model is. But you might, it could be that you take a long window and you don't want to be all these. Maybe you look at the differences between these time points instead of the actual raw time points. And there's actually these low-dimensional patterns that may oscillate in some way. So if you look at these, there's kind of this pseudoscience of day trading, and they look for certain patterns in these things. And there may only be kind of these kind of lower structure of these patterns, but you might have 100 time points, but there only might be like a 3-dimensional substructure of these that you would try and pick out. So I'm not going to comment too much on so day trading, although yeah, I just don't say anything about it. Okay, and then fourth example would be, so let's take pictures of a moving object. Okay, so let's say there's a picture of like the Utah teapot. This is kind of a famous 3-dimensional little thing in computer graphics. And one common thing that people would do, they would try and, one thing that happened here at Utah at the beginning of graphics was they made a 3-dimensional model of this teapot. And part of how they did that, and there are other ways as well, but they would take pictures of this teapot. Okay, and a picture is going to be a series of these pixels. And so you can think of each of these pixels, P, R, C. This is just going to be a value. And for simplicity, let's think it's black and white. And so this value has a value between 0 and 1, or maybe 0 and 256. Right? So it's usually an integer between 256, but it's think of it as some scalar value. Okay, and so now if I have the number of rows and the number of columns, then my D here of every picture is R times C. Right, so if it's, what is the case here, like 8 rows and 12 columns, then I have, then I've got 96 dimensions here. Okay.
Oh, this is where you're laying them all out on one line.
Yeah, so I've kind of, you could think, it looks like a matrix here, but really the matrix, at least at this point, is not giving me, I'm not using that structure, that this pixel is next to this pixel. Now in computer vision, they actually use this structure more so sometimes, but sometimes it's ignored. And internal to a representation, this will be stored as a single vector, not as a matrix. Or the matrix, which is actually stored as an array internally.
So then can we think of like PCA as like getting a slice of the overall?
Well, so that's not what PCA is doing here. I'm kind of, in this example, I want to say, I'm going to take, this is one picture, but I want to say move, and by this I mean like rotate the teapot slowly have it on a turntable and rotate it. And I might also change like, so there might be some source of light, right? I'm going to change the amount of light. And I'm going to change the light, and I'm going to take more pictures. Okay, so I'm going to take n different pictures where it's a fixed teapot, and all I'm doing is I'm rotating the teapot and I'm changing the intensity of the light here. Okay, so each picture is going to be a d-dimensional vector, and I'm going to get n of these pictures. Okay, so n pics, each AI is going to be in RD. Okay. So what's happening here is I'm getting these d-dimensional vectors, and they're n of these pictures, but really I'm only changing two parameters, the amount of light and the angle of rotation here. So it's really, there's a constant scene here, but there's two parameters I'm changing, so should be implicitly to describe which picture I took, I really only need these two parameters. Can I somehow represent these vectors in a two-parameter space? Right? Okay, so in general, what PCA is trying to do is define this low-dimensional subspace. In here, it could be this parameter space. And in here, it could be some kind of these low-dimensional patterns that are happening on, like, across, maybe these are hourly or daily stock prices over many days. And this is, well, it's used in day trading. It's also used in real economic analysis, in various other forms of the market. In here, there's usually, there's n reason D people, but there's only some limited number of actual real categories of movie and types of kind of preferences that actual people have. We want to uncover this low-dimensional structure, and in this weather station, there's big storms that move across the country, and they change the weather like overnight, and there's correlation between stations. If the one downtown changed, then probably it's likely the one, other ones around at the airport or at the university are going to change. Their temperature is going to drop around the same time. And if the temperature at the airport is really hot, it's probably going to be pretty hot, but not quite as hot at the university. Okay.
So why is having the data in a low-dimensional subspace, like, why is that useful?
Yeah, so why is it useful? So we'll see a couple things. So one reason is that so this is a good question. Why? So if low equals 2 or 3, then I can draw a picture, right? So if I have data in this high-dimensional subspace, it's hard to understand going on. And as we've seen in various things throughout the course, I've been able to draw pictures of what's been going on, and hopefully that's been helpful. If I'm in high dimensions, I can't draw pictures. And so there's often this idea of reducing it down to a lower dimensional space, and then you can kind of visually see what's going on. If it's 100 dimensions, it's going to be hopeless. Right? There are techniques from, if you take the visualization for data science class, that maybe get you up to 6 to 10 degrees, where you show a bunch of different perspectives all at once. Those already have their drawbacks, and there are these other things like parallel coordinates that you can also try. But if you have a 2 or 3 dimensional picture, that's very helpful. So can I get this down to 2 or 3 dimensions? Another reason is that it's the kind of core structure of what is going on. There's something that I'm hoping there's the real model of what's actually happening is captured in this kind of lower dimensional subspace. This can be useful to kind of think about and model, like I can think about types of movies with lying on this low dimensional subspace. There may be horror movies, there are rom-coms, there are documentaries, sports movies, and they probably don't need a 1,000-dimensional space to describe all these, or really what's going on, to help me think about this more. And so sometimes this allows me to remove the noise of what's going on here. Okay, so I think that that if I push everything down to the 4-dimensional subspace, the part that I'm missing is the noise part. And so it makes it more robust in the predictions if I use a prediction just in the low-dimensional subspace. There was a talk at the Day Science Day where they did this with this really noisy astronomy data. And one of the best solutions they have is to take this, and they found this through a 4-dimensional subspace of these 4,000 dimensional vectors, and these kind of help them kind of figure out what, they have a model that works in the subspace, but they couldn't possibly learn a model in a 4,000 dimensional subspace. So they can model it within the subspace, and it kind of helps them filter out noise that comes from all sorts of places. And then finally, so sometimes there are some algorithms we'll want to use for analysis that will depend on the dimensionality d here. Okay, so if this dimensionality becomes high, it's often the runtime might be exponential in this variable d here. And so if we can reduce d, that reduces the exponent of the algorithm, and this can be a big improvement. And this happens in numerous places. So if we can do this process quickly, it makes the whole algorithm speed up. Okay, so those are kind of the three main reasons. We won't really touch on this one. I'll mention some of these. Was it that same question you had, or?
No. It was going all the way back. So, like, what's this DP pool? Is it just like the DP column would be one specific person?
Yeah.
Okay.
Right. So everyone with these, there's lots of missing data, and there's other issues that come up. But
so not every person's watched every movie.
Yeah. Unless they're a movie critic, they probably haven't watched every movie. Yeah. But you can kind of there are techniques actually using the same machinery we'll use that helps you fill in the movies that people didn't watch as well. Yeah, so it's all related to these ideas. So this will be part of removing noise, and that will help fill in missing data as well. Yeah.
So if I had a bunch of data that was in high-dimensional space, and I wanted to express it in lower dimensions,
Yep.
my first idea would be to run a regression. Maybe you could do like a regression with 2 variables or something, and if it fits really well, if I just express it there. My question is there a difference between principal component analysis and something like that?
Yeah, there are a few differences, and this will be a lot of the rest of the next part of the lecture.
Okay.
So we'll talk about this. So, if you're doing just a regression, this is basically going to, I can draw a 2-dimensional picture, and this shows you some of the difference, but will also hide some of, and it will hide some of the difference too. Okay, so let's say I have some data points, okay, and my goal is to fit. In this case, it's going to be a low-dimensional subspace. It's going to be a line through here. And what regression is doing is that it is going to try and fit something that minimizes the sum of these vertical distances. Okay? So regression has vertical residuals. Okay. PCA instead, this is a new purple marker I found in the supply closet this afternoon. So the PCA is going to have orthogonal so residual. So I'm going to map every data point here onto the closest point on this line, not the closest point in the y direction. Okay, so this is one difference between regression and PCA. Okay, the other difference is that regression is giving me a function from, say, RD to R, from X to Y. Okay, so this means from every point on X here, every point on X, it maps up to a point on Y. So if, as this gets to a higher dimensional space X, Y usually stays one-dimensional, and I'm fitting this red space here, which I've only drawn one dimension, becomes multi-dimensional, but it stays a d-dimensional space in a d plus one-dimensional domain. If this is RD and this is R1, then it becomes a d. I'm only going down one dimension. Where typically PCA, I can go down multiple dimensions. So it's PCA is basically a map from RD to RK, to a k-dimensional subspace. So I can go down to, say, 2 dimensions from 1,000 dimensions. Or in this kind of astronomy example, from 4,000 dimensions down to 3 or 4 dimensions. Where regression is not telling me how to do that. I kind of get down 1 dimension instead. So I usually want to go down many more dimensions here. Okay, so those are, that's PCA here. Okay, so another important aspect of this picture, okay, is that there's something important about these examples here, these data matrix examples, and this is the property that, let's say, all coordinates have the same units. Okay? So I had examples with regression where I'm like predicting the weight from the height, stuff like that. Or I was recording stuff on this website and I recorded like the jiggle of the mouse, the amount of time I spent on there, and the amount of scrolling. These are measured in different parameters. They meant different things. All of these examples are not like that. They're all, in this example, every coordinate is a temperature, right? This is a temp at every coordinate. In this one, it's always a rating. In this one, it's always the stock price at every single coordinate in the matrix. In this one, it's always this black and white value. Okay, so I've always have the same units. Every single element of the matrix represents the same sort of quantity. I can compare them. Okay, and this is important because in the regression, I'm trying to predict one value, and so kind of the coefficients kind of change my units for me individually in some nice way automatically. It's learning how to map one kind of quantity into another with the coefficient. In here, I'm measuring this distance from the data point onto this line, and this distance is going to be the Euclidean distance. So now this is AI, and this value here is going to be pi, we're going to call this f of AI, and I want to minimize this distance AI minus pi of f of AI. And this is Euclidean distance. What is this doing? I'm going to, this is going to be a sum over j equals 1 to d of AI minus j minus pi f ai j squared. Okay, so I'm taking the coordinate differences in each of the different kind of d-dimensional coordinates. I'm squaring them, that's kind of fine. But then I'm adding them up. Okay, so if I'm adding height, squared height, and squared weight, the quantity, the sum of a squared height and squared weight doesn't make sense in terms of units. Okay, and so if I change the measurement of height from inches to feet, it changes the dynamics of the relationship between these two. So it changes this distance structurally when I change my units. It no longer makes sense at all to do this. So if these do not all have the same units, they're not all measuring the same thing, this whole thing does not make sense. Okay, it's built on kind of this idea that I can measure this closest distance, and I'm not, this whole computation is kind of a nonsensical thing. I'm mixing units together in some weird way.
The pi is not a product in this case.
The what?
The pi?
It's not a product, it's going to be a projection. This is from a dot product, and I'll review this in a second. Yeah.
If you are measuring different things, but standardize them or normalize them in some kind of way, is that acceptable?
This is what happens a lot. What people do, they get results from it. Sometimes it's useful. I don't really know what it means or what's going on under the hood. You're kind of at the whim of outliers in various ways that affect what your normalization does. And, and you've destroyed a lot of the kind of the variance structure, which is the key thing that you're going to try and be pulling out here. So you can do it, it's not uncommon to do. I don't know what it will mean when you actually do it. I would downright tell you just not to do it, but you may get to a point where you want to do some dimensional reduction and you're like, well, I need to do something, and then maybe that's what you should do. But it's not necessarily going to be meaningful the same way as if your input is going to be one of these data matrices.
Just for like context, the thing that we can't do is have a matrix that has like n customers and then d attributes of those customers like in their profile. So like their gender, their like, how much they pay for, stuff like that. That's something that this dimensionality reduction can't help us with.
It's not going to magically solve this. Tell you how much am I supposed to weight the time they spent on the website versus their age. You choose some way of kind of normalizing this, and then you can look for relationships, but I'm not sure what's really telling you. Things like regression and versions of classification are going to kind of be agnostic to this. Not all versions of them are. There's like, if I do a regularized version of regression, you're at some point going to be throwing a norm in there, and that norm has the same issues. If you're doing classification and you're measuring it based on the distance to the margin, and we'll talk about these things later in the semester, then again, that distance is going to be Euclidean distance, and it may not make sense. But if you just want a separator, it'll be fine in some way. So there's some parts that make sense with these mixed unit things and some that don't. It's very common to mix units, and sometimes this causes weird behavior, and it's going to be subject to the choice of feet versus inches or centimeters, and just something to keep in mind. Yeah.
Is it possible to give like an example of what kind of weird behavior it would end up exhibiting?
So, like, we haven't really gotten into any techniques yet, so it's hard to kind of go into much detail now, but I can try and explain more later. But it can completely change what the result is of your PCA. It can like give you things that look completely, totally different by just changing from feet to inches, you know, in your stuff, or adding in one outlier or removing that outlier. And that changes how your normalization works. So even if I have a version that's robust, if I chose to normalize first, then it's going to change the normalization, and that's going to change the results. So it makes it very susceptible to outliers, when otherwise it's not so susceptible. I mean, it still has issues with outliers, and that's another story. But yeah. So okay. So there's other things that in the data mining class we talk about, these distance metric learning, which is trying to learn how to weight different components, and does that in a way that's automated. You need to throw in extra information to use that to learn this information. You can't just automatically do it with kind of fancy kind of linear algebra as we'll see next. Okay, good. So in order to okay, so I should, the foundations class, I have to actually define what the problem is we're solving a little bit more clearly. To do that, we have to go back to a projection, and this will be this pi of f operation here. Okay, and so we're going to start with a unit vector u. This will be in Rd such that the norm of u is equal to 1, right? And so we're going to start where, let's say, this subspace that we want to project everything onto, and we're not getting to kind of determining what the subspace is yet, but let's say we have a subspace. Let's say it's 1 dimension. Okay, so we're going down to k-dimensional space. Let's say k is equal to 1, and so I have this unit vector, and so if I have now some data point ai, the projection of this, the orthogonal projection onto a point here, which I'm going to call this point pi view of ai, is going to be defined through the dot product. Remember, it's a unit vector, and we're going to say it starts at the origin. Okay, so then this pi view of ai is going to be defined as the dot product ai of u. Remember, that gives me the length along this direction of here, and I want to move that length in this unit vector direction, so times the vector u. Okay, so this is giving me a point still in Rd, right? Because u, this is a scalar value, the dot product, and u is a vector in Rd. Right, so I'm getting a point back in Rd. This is the point that lies along the direction u, and it's just scaled by the amount of the distance of ai along this direction. So this gives me this orthogonal projection. That means this is a right angle here. Okay. So now we want to generalize this to a k-dimensional subspace. Let's say f is so k-dimensional. Okay, and I'm going to say it contains the origin 0. Okay, so it contains the origin. In class next week, we'll see how to handle the case where it doesn't contain the origin. That's kind of a small change from everything else we're doing. So for now, we'll assume it contains the origin. Okay, and so in order to define this, I'm going to have this orthogonal basis, u1, u2, up to uk, and this is going to be an orthogonal basis, which is going to mean that each ui is going to have a norm equals to 1 for all pair I not equal to j, then the dot product ui uj is 0. So they're going to be orthogonal to each other. Okay, and in particular, for all x in f, then I can say x is going to be equal to alpha I in this way. And this turns out this is pretty important here. So what I can do is I can represent it as a dot product with some ui. Where's this? So as each alpha I times ui, right? One of these basis elements. Okay, so I can represent every data point that's in the subspace as a sum of a scalar alpha I times this vector ui. These are orthogonal vectors, and a particular alpha I is going to be ui dot x. Okay, so this is an extension here of this one-dimensional projection operator. So this is going to, so I'm going to find this k-dimensional projection operator. Pi of f at alpha I is going to be the sum of I equals 1 to k of ui x times ui. Okay, so now instead of just a single term here, it's going to be a sum of k of these terms, and they're going to be orthogonal, so they're going to compose this together, right? And so this will be another point in RD, because adding together a bunch of scaled d-dimensional vectors. Okay, so what does this look like? Let me try and draw a picture here. So I'm going to have this subspace F, okay, and this is going to contain the origin in the subspace, and I'm going to parameterize this by, in this case, let's say this is a picture in RD, and I'm going to have U1 and U2. And so if I have some data point here, which is somehow kind of, think of this as slicing through the board. This is not on the board so much. And so I'm going to project down to a point here. This is going to be pi of f. This is of, let's call this x here. And so this blue data point is x, does not lie exactly on the subspace F here. And I get this projection by basically thinking here okay, so I'm projecting down here, and it's going to have these two coordinates in this plane here. And this hard to draw in 3D. I've done a little bit better job in the book, hopefully, but yeah.
So we're in the part where we're summing from I to k, I equals 1 to k. Is each I in there? Is that each like that's basically defining where it lies on that coordinate?
Yeah. So it started. Think of here, x started as having 3 coordinates here: x, x1, x2, x3. This is in R3. And now basically what I'm doing by having this subspace F, which is 2-dimensional, k equals 2 here, is that I'm giving it a new 2-dimensional coordinate system. Okay, if I had chosen U1, for instance, I could have chosen U1 as E1, which is 1, 0, 0, kind of E2 as 0, 1, 0, and E3 as 0, 0, 1. And if I use k equals 3, I basically recover the same coordinates here. These are all unit vectors that are orthogonal to each other. And this recovers the same basis here. What I'm doing is I'm choosing a new basis that happens to be lower dimensional. And now I can write this as two coordinates here, alpha 1, alpha 2, where alpha 1 equals x u1 and alpha 2 equals x u2. So I can think of it in this two-dimensional coordinate system, but as I've written it here, it's still a three-dimensional vector, right? Because I'm embedding it in this three-dimensional space. But all the points in this projection I can describe them with only two coordinates.
Okay.
Is that?
I think so. I think I'm seeing that. Yeah, pretty sure.
Okay, I mean, so this is an important kind of conceptual thing that's going on here. I'm taking something from a higher dimensional space, and I'm putting it in a lower dimensional space, and well, they're still full dimensional vectors when I do this operation, because I'm adding together d-dimensional vectors that are just scaled. However, there are only k of them, in this case only 2 of them, so all these objects which I've projected to, I can describe with only 2 coordinates, or in general, k coordinates. So there's a new coordinate system here I can use to describe them. And because there are only k of them, it must be a k-dimensional subspace.
These new points that we're creating are they full representations of the original point, or are they approximations given the subspace?
Yeah, so it's different. This point is not the same as this one, right? So if x is on the subspace F, then it's a lossless transformation, mathematically, computational roundations. But if it's not on the subspace F, and I have to project it to someplace else, then it's a different point. There could be 2 points, x and say x prime, that get projected down to the same spot. Right? So I've lost some information. In particular, if x prime is equal to pi of fx, then, and this is not, then I've lost information. Yeah.
So it's a little different than, this would be a whole other idea, but we're not just basically just taking a dimension off and we're not just like slicing it. We're not doing that. We're essentially keeping some of the information from the third dimension when we reduce it down to 2.
Yeah, I'm not. Yeah, so again, why it's important for them all to be the same unit. We're not prioritizing one dimension over the other. We're taking a linear combination of the dimensions. This dot product operator, remember, this is kind of taking, this is again a sum over the d dimensions here to get the scalar value. Right? So alpha 1 is a linear combination of all d coordinates, and so is alpha 2. They're different linear combinations. But so each of these blends information from all d coordinates. And you shouldn't, kind of conceptually, you should think of it as the slice. The slice part is what is left. I'm projecting onto the slice. I'm not carving away so much. I'm reducing the whole dimension of the space. So I'm kind of changing the whole concept of measuring. So it's not like trimming off a piece. It's kind of squishing down. Is kind of the right way to probably describe it or think about it. Yeah.
So if F is 2-dimensional, our data space is like 3-dimensional. Are we doing, is that a k-dimensional? Is this a 2-dimensional projection or a 3-dimensional projection?
Yeah, so in this case, this example has k equals to 2 and d equals to 3. So I would say it's a projection onto a 2-dimensional space. But technically, it's a non-one-to-one map within R3, right? It's an, I guess, okay, it's right, an onto map that lives within R3, because all the vectors still live in R3. Although if I just use the alpha coordinates, then it goes down to k dimensions. Then it's a k-dimensional projection. Okay, so this is what a projection is doing. Now, the goal is to find not just any projection, but I want to find one that's good. Right? So I want to find a good projection to a k-dimensional space, or the best projection. All right, so now the goal is to find F star, which is going to be the arg min F, which is going to be k-dimensional cells subspace. Okay, so I haven't built up the complex notation to describe this, but to minimize the this way, sum equals I equals 1 to n, AI minus projection of F, AI, okay, squared. Okay, so I want to find this subspace F star, which is k-dimensional for some value k, or for all values k, which minimizes the sum of squared errors. And the sum of squared errors are now measured in this orthogonal projection. The distance from the original point to the orthogonal projection onto F. Okay, so this is the goal of PCA. Okay, and then this subspace F and some other information is going to encode a lot of information about the data set A, this matrix A. And I guess I call this in some places the sum of squared errors, or let's say arg min F of the sum of squared errors of F. Okay, so before, again, it's a sum of squares error formulation. If I wanted to do, I could take the average and I could take the square root afterwards, and that'd be the root mean squared error, but it would be the same kind of, they would have the same min there if I wanted to do that. Okay, so how could we possibly solve for this? Seems like it took me a long time just to define properly what the actual kind of solution is. How do we solve for this? Yeah, so a good idea of how to do this would be to set up a gradient descent formulation and solve it. We just have this section on gradient descent. It turns out that, unfortunately, this kind of F requires this U of F, which is U1, and which requires that each UI is equal to 1 and spread. So we're going to define F through this basis, and this basis requires the orthogonality turns out is okay, but the requirement that it is exactly norm 1 is not so convex. If I just look in 2D, so if I look in R2, then U must lie on the circle here. Okay, so the only allowed solutions, you know, I can't be out here or in here. I can only be on the circle, which means that if I take 2 points and I take the midpoint here, this point is not allowed. So this solution space is not convex, and that basically means you can't directly use gradient descent here. You can do something called proximal gradient, where I take a step and then I renormalize at every step, but that turns out that's not the right thing to do either here. Or at least there are solutions which are better. We'll effectively do things where we'll start with the direction and it will get bigger and bigger and bigger, and then at the end we'll project it. But okay, yeah. So what we're going to do is we're going to use the magic of linear algebra, and we're going to use what's called a singular value singular value decomposition, SVD. Okay, this is so who's heard of this linear algebra operation? Okay, so and who hasn't heard of it? Okay, so you got through linear algebra without hearing about singular value decomposition. Every time I hear that, I'm like, why aren't they teaching this? But okay, so good. So this is basically the solution of PCA is encoded in the singular value decomposition. Okay, and we'll go through and explain this starting now, and then on Monday next week we'll see how to compute the singular value decomposition with the power method, which is one way of doing it. There are other ways, you know, and it's useful to see how it's computed, and that tells you some understanding about the robustness of it and various other properties. But for most purposes, until you get pretty deep in the weeds of what you're doing with this, you can treat this as basically as a black box. Okay, the 99% of the times you'll actually call this in data analysis. No matter what language you're going to run this in, you're going to use the same code written in Fortran in the 1960s or 70s. There's some libraries people super optimized for singular value decomposition in, I think, the 60s or 70s, and we still use that code today, or slight modifications of them. There are these libraries that all languages kind of basically link to. At very large scales and some approximate version, things change, and the data mining class will talk about some of these issues. Okay. But for the most part, including Python, treat this as a black box of how to compute it, but not what it means. Okay, so I want to talk about what it means instead of so much how to compute it. Okay, and so the input is going to be some matrix A in RD. Okay, we're going to talk about this, and then we'll almost solve this problem, and then Wednesday next week we'll actually solve this problem. There's a slight difference in that. We've assumed it goes through the origin. I don't want this to assume to go through the origin. So PCA will remove the assumption that the solution goes through the origin. Okay, so the input is going to be this matrix, which is n times d, and the output is going to be 3 matrices, U, S, and V transpose. U is going to be in R n by n. S is going to be in R n by d, and it's going to be so it's going to be a like special diagonal matrix, and V transpose mean R. So D by D, these two are going to be orthogonal. Okay? So U and V are orthogonal of N by N and D by D matrices, and this connects them. It'll have the property that A equals U, S, V transpose. So it's a decomposition of A into 3 matrices, U, S, and V transpose. Okay. Actually, V is, it doesn't matter. But, okay, so this is, although this is not true in Python, Python gives you kind of compressed versions of the matrices so that if you just take the output and multiply them together, you don't actually get this. But in like MATLAB or C, you'll probably get this.
So you use the Moore Penrose pseudo inverse for this?
The SVD kind of essentially tells you how to compute the Moore Penrose pseudo inverse. You're not doing the Moore Penrose pseudo inverse. You can do that by inverting U and V are orthogonal. So that means their inverse is their. So if I want to do an inverse, I can change the order of multiplying them and invert all the matrices. U and V, that's just a transpose. S is diagonal, so it means just doing an inverse on these terms there. But if the rank is too low, then I just keep them 0, and that's the Moore Penrose pseudo inverse. So this tells you how to compute the Moore Penrose pseudo inverse. So one of the things you get out of the SVD is how to compute an inverse or a pseudo inverse. Okay, so that operation we need for linear regression I said was kind of closed form. This will tell you how to compute it once we put all the pieces together. Okay, and yeah.
Bother you real quick? I need to leave some materials for the next class. Can I just kind of make a reference for like a quick second?
You'll leave them up there? Is that sure? Yeah.
Okay.
Sorry about that. Yep. Okay. Good. So, all right. So this probably doesn't help very much to see this. What I find most helpful is to draw a picture. A is going to be this rectangle, N by D, and what I'm doing is I'm decomposing it into these 3 matrices. We're going to say U, this is U, it's going to be N by N. Okay. Then I made these a little bit too big. Let me make this a little bit smaller. Okay, so U is squared, that's N by N. S here is N by D. And then V transpose is going to be D by D. Okay, so these two are square, U and V. S is diagonal. What does diagonal mean? It means that there's going to be information here, S11, S22, S33, up to SDD. This is all information. This is all zeros. This is all zeros, and this is all zeros. Okay, so S is almost all zeros. It's just a bunch of scalars. Okay. Okay, so I'm giving this decomposition. I'm writing A in terms of these matrices. Okay, let's kind of talk through what these matrices mean. Okay, so the first insight is that the S matrix is all zeros, especially down here. In fact, in Python, it won't even give you this part of the matrix. It's useless. It's all zeros. What that means is that anything I multiply this part by over here, this part of the matrix gets multiplied by these rows, is kind of uninteresting. Right? So this part here basically says, you know, it doesn't matter what's in this part because they're going to be multiplied by all zeros. Okay? Okay, that's the first insight. Okay, the next interesting thing about this, there's more structure I haven't told you about yet, but okay, so the next interesting thing is I'm going to get these columns, we'll call this UI. This is going to be called, UI is going to be the height left singular vector. Right, remember U was orthogonal, so all of these column vectors are going to be orthogonal to each other, and they're going to be, these are going to be unit vectors. Okay? And the same is true over here with V transpose. I've done the transpose, so it's going to be the row vector here. So Vj, this is going to be the jth right singular vector. Okay, and this is a vector in Rd now, and these are all going to be orthogonal to each other. Okay? And so it turns out that the when I multiply a vector, right? If I remember now that if I take some vector in Rd and I multiply and I look at V transpose times x, this is going to have the same norm as x. Multiplying by an orthogonal vector, or orthogonal vector transpose is still orthogonal. It's not changing the norm. I'm going to have d orthogonal vectors. Basically what I'm doing is I'm doing this kind of, I think of these u values as being these orthogonal vectors, but instead of just having k, I've got d of them. So that means I always recover exactly the same point. I'm just changing the basis I've written this in. So I'm basically getting out another d-dimensional vector, but now its basis elements are alpha 1 up to alpha d. But if I multiply through to get the projection, I'm getting the same point back. So if I'm doing this, I'm just getting the alpha coordinates, but I know it's actually the same point as here. So I'm not changing its norm, I'm just changing its coordinate system. So this is norm preserving. So multiplying an x vector through by V transpose is not changing the norm. The same thing will come out here. Multiplying by u will not change the norm. The only thing that changes the norm of the vector is this S matrix. So this has all of the norm, the scale information. So the S matrix, think of this as all the scale information. And these objects here, I'll call the third, or in general, the ith singular value, right? So the ith value is the ith singular value, and that contains the scale information. Okay, so if I get a vector x, and I can also look at the S V transpose x. This is not the same as the norm of x. So now when I multiply by this x, this S value, that's where I'm changing the norm of what's going on. Okay? I'm changing the basis, and then I'm changing the norm. What's convenient about this is that this scales it on the coordinates, right? S11, the first singular value, is changed telling me how to scale the first coordinate, this the second coordinate, this the third coordinate, but they're the coordinates in the new basis. Okay? And so what is kind of going on? It has this property that S11 is greater or equal to S22 is greater or equal to S33. So these are all decreasing, and these are all greater or equal than 0. Right? So the singular values are decreasing from largest to smallest. So that means when I multiply x through here, I'm changing the basis, and then I'm scaling. And so the first right singular vector is getting the most scale. That means it's the most important of what's going on here. Right? So the most important direction is from the d-dimensional side is the first right singular vector. This has the most scaling effect in the data. So, okay, so I'm gonna, just because I have this all on the board, I'm gonna tell you this, and then we'll walk through this more on Wednesday. Yeah.
S11 is greater than or equal to S22 and so on. Is strictly greater than 0 or greater than or equal to 0?
Yeah, so they could be equal to 0.
Okay.
And the property, actually, the largest index, which is non-zero, is going to be equal to the rank. Okay, so I'll come back to this in a second. I just want to preview you to something we'll talk about more on Wednesday. I'm basically going to, these are going to be the first K right singular vectors. So U of F will be equal to VK, which is V1, V2, up to VK. So this will give me the best subspace. Taking the first, or the top right singular vectors. If I want to project, if I want to think of these as endpoints in d dimensions. If I want to think of them as d points in n dimensions, I use the left singular vectors. There's some symmetry going on. Okay, but we'll talk more and think more about this on the more properties of this on Wednesday. Yeah.
There are methods for choosing K, or is K just kind of arbitrarily like, it would be nice if I had 5 dimensions?
Yes. There are methods for choosing K. They're kind of heuristic-y. And you usually do just say, it would be nice if I had 5 dimensions or 3 dimensions. You kind of want to look at, basically the short answer is you want to look at the decay of these singular values. And when they start getting really small, you stop. That means if they're pretty close to 0, it's probably noise. There are a variety of different techniques in different settings. If I want to use this for predicting these time series of data, I do some kind of cross-validation statistical tests on the value k to see which gives me the best prediction, for instance. In here, we're just finding the structure, and it's, but this gives me all k of them. I have all of them, and I can choose afterwards. Right? So my method is not predicated on knowing k ahead of time. When I call this black box within Python or MATLAB or wherever, it'll spit out all k. Or there are methods that give you all d of them. And sometimes I can say, well, I don't need all d, and d is really big, so give me first 100, and then you might still only choose, say, 45, but you're pretty close. Yeah.
So when you were talking earlier about how like unit confusion can completely mess up our resulting subspace,
Yeah.
is it like in that V transpose vector that we get like wildly different rows and column like values, like magnitude and stuff like that, and we start to get these weird subspaces?
Yeah, so all the magnitude is going to be captured in here. Like if the units are very different, so the magnitude is very different, probably just the first subspace will go along with that first unit, right, that had the really large values. And I'm not really telling you much about it. It's not clear what it actually means anyways in that context. I'm measuring, it's something about measuring the residual distance of these errors, right? Measuring Euclidean distance, and it's not clear what that Euclidean distance means. So it tells me something. It'll tell you something about covariance, but that covariance has been kind of skewed in some ways by the scale. So it's still being kind of hidden in some way there. So okay, let me actually just end by just, maybe I'll, for the last 4 minutes, instead of trying to put something else on the board, I'm going to try and just go through a very quick example. Okay, so here's how you would do this in Python. Import SciPy and NumPy. SciPy, remember, has the linear algebra package in it. Okay, and I've got a very simple matrix A here. Okay, and I call linear algebra package the SVD operation, and this gives me, I can turn this on. This gives me somewhat fuller matrices. Okay, but I turned it false for now. Let's see what it, and I think this is the default setting. And so it gives me U, S, and V transpose. And in Python, I wrote S as a lowercase because it gives you a vector. Okay, so U gives me this. This is not the full matrix. It's only 2 by D. Remember, there was that after D, that part was uninteresting anyway. All it did was ensure that these rows were going to be orthogonal, or that the other columns had to be orthogonal with these columns. But it was not doing anything interesting. If I instead turn this true, truer, okay, and then I call this, I'm going to get the full matrix. But these 2 columns here are not meaningful. So let's turn them off. Okay, and print U. Print S is just giving me this vector. It just cares about the diagonal elements 8 and 2. This is a pretty decent drop off, but not huge. You'll see other matrices where this drops much more between the singular values. And then the right singular vector, this is V transpose. It gives it to you as the transpose, but now the rows are what's interesting. Okay, and so what was that? Okay, so now I can take some unit vector X. Well, it's almost unit vector, but I'll force it to be unit vector. And then I can multiply it by V by V transpose here, and I get this back, and I can check exceed
LA dot,
yeah.
or whatever it is.
Yeah, okay, so the norm it gives me back as 1. Okay, so good. So it hasn't changed the norm, and this had to be, because I divided by the norm, so it had to be norm 1. Okay, but now if I multiply it, now this is a way to get the full diagonal SVD matrix S that I needed here, and now I multiply my XC, my output, and I get eta. This is notation from the book. And now the norm here is not 1, right? Print. So this is not norm 1 anymore. This is where scaling has happened. I've scaled along the coordinate axis, and I'll draw some pictures on Wednesday that kind of illustrate what's going on. And then I multiply by u, and what's happened is it's gone from a 2-dimensional vector to a 4-dimensional vector. Remember, a was 4 by 2 dimensions, so if I multiply by a dot x, the original vector here, I should get the same thing here. So it's a transformation from a 2-dimensional space to a 4-dimensional space, and so u needs to do that. I need to go from this 2-dimensional vector to a 4-dimensional. In fact, S probably did that in most languages, but in Python, that's encoded in the compressed version of u. And just to check, if I multiply these all together, remember this was the expanded capital S here, I get back my original matrix name. So it is a decomposition. Okay, but this is a built-in thing, and we'll see one way how to compute it on next week. Okay, great. Get the homework's due on Wednesday.
I'm working on it right now. I started last minute, but I think it's super fun.